Hi, welcome back. This time we're going to be discussing what happens if you have a function of more than two variables. So we've been talking up to this point about a function that looks like f of x, y. So we take in variables x and y, and we give out maybe a value z. Well, we can easily come up with some functions that have more than two variables. So you have some n number of numbers, and the output is one number. A simple example that you deal with on a regular basis is when you go to the grocery store. Consider the function f of x1, x2 up to xn to be equal to cx1 plus cx2 plus dot 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 plus cxn, where these c1, the c2, the cn, these are maybe the cost of each item that you put into your basket. And then the x1, x2, xn are the number of each item that you put into your basket. You go to the grocery store and you decide you want 2 cartons of milk. Then the cost would be the cost of the milk, and you would have 2 of those in your basket, and those would both contribute to the cost that you had to pay for your full basket of groceries. So if you're trying to think about what the graph of such a function would look like, it's going to hurt your brain, right? So how did this work in a function of 2 variables? We had a domain, and then we drew a surface on top of the domain. But now the domain is either in 3 dimensions or higher. 4 dimensions, 5 dimensions, it's really hard to think about that. And we need an additional dimension to draw the graph of it. So we can't visualize the surface, which is the graph of the function when n is greater than 3. When n is equal to 3, what we can understand is the level surfaces of f. So we were talking about the level curves of a function f of x, y. Here what we're doing is we're talking about places in our domain that have the same function value. So where is the function equal to a given constant? So consider this function. F of x, y, z is equal to x squared plus y squared plus z squared. So it's saying choose a point in 3 space. So you're in this room and you're trying to see, and there's some center of your point, the center of the room, and we can talk about what's the square of how far away you are from that center point. And then this would be an example of that function. It would be, okay, we take where I am now, look at the x-coordinate, the y-coordinate, and the z-coordinate there, square them all, and that is a function that will give you the distance you are from, the square of the distance of where you are from the origin. And so what would be the set of points that all are the same, have the same function value? They would be the points that have the same distance from the origin. So they would lie on a sphere. So for instance, right, this red sphere are all the points that are the same distance as any other point on that sphere from the origin, and because of that, their value for this function is the same. I think an even better example of for understanding level surfaces is the function that measures the temperature of every point in the room. So it's probably a warmer temperature near the ceiling. It's probably a colder temperature near the floor. It's winter time right now, so probably near the doors it's probably colder, and near the center of the room or near where your heater is, it's even warmer. And so if you so this is a function that depends on the temperature of your height, of your length, and your depth of your position, your x, y, z coordinates of your position. And at every position, it's a different temperature. And so um, the question of what a level surface is if you're at your point, look at all of the different places in the room that have the exact same temperature. And what you're going to see is you're going to see like a bunch of like thin sheets that are surrounding the doors or surrounding the heaters that measure that everything on that surface has the exact same temperature. So that's what these level surfaces represent. They represent where is the function value exactly the same along that whole surface. All right, let's talk about how we can use Mathematica to understand functions of three variables. So just like before, when we were when we wanted to understand the domain of a function with two variables, we used the region plot command. But now, when we're talking about functions of three variables, f of x, y, and z, then our our function, the domain, is not going to be a set in 2 dimensions, it's going to be a set in 3 dimensions. So let's look at this example. Square root of 2 minus x squared minus y squared plus z squared times ln of z plus 1. You plug in a triple, x, y, z triple, you plug it into your function, and that's going to give you an answer for some choices of x, y, and z. So what does that set look like? So we'll plug this into the region plot 3D command. And so just like before, we have to specify, okay, we want that whatever inside the square root is greater than or equal to 0. And whatever is inside the natural log has to be strictly bigger than 0. So we run the region plot 3D command, and we get this region. These are all the set of points that you can plug into this function. I've used this plot points command to make it even smoother, so we can see this at a little bit with better resolution. And then we were talking about level surfaces, right? So a level surface, if we're thinking of this as being like this orange is hot and this green is cold, you can sort of think, okay, so on this side of the room it's cold, and then everything in this green surface is the same temperature, and then everything on this blue surface is maybe average temperature, and everything on this side is hot. So this would be a way to just see how is the temperature, or what's the gradient of the temperature as you move through the room. So just like before, if you want to just specify one value for your function, you can. And if you want to specify what the contours are going to be, exactly what the numbers for multiple ones, you can specify those as well. And it starts to give you a better feel for what the function really is and how it behaves. All right, so let's stop there for now. See you the next time.